Okay guys, Chapter 9, Floating Point Operations. This will be our last topic for this semester unless we get going really well and have a little bit of time to talk about recursion. However, before we get into floating point instructions, let's talk about the floating point unit itself. There is a separate processor in most modern day computers called the floating point processor, or the FPU. Nearly independent of the CPU, it has its own registers, it has its own instruction set. They do share random access memory. So in addition to that, the registers from the CPU, remember we had 4 general purpose registers, 4 index registers. Well, the floating point unit has 8 80-bit or double precision, extended double precision registers organized as a stack. Let me just draw it this way. Organized as a stack and operates as a stack. So most of the instructions are going to operate on some part of the stack, where the top of the stack is the stack top, or could be numbered register 0, stack top, or stack 1, stack 2, and so on. So there are our 8 registers. Things get pushed on the stack, things get popped off the stack, just as they would in a stack data structure. In addition to these 8 80-bit registers, we also have several 16-bit control registers, including the status word. Now, before we go any further into instructions, let me just point out a few notes about each one of these. Each of the floating point instructions is going to be prefaced by the letter F. This indicates, so float load, for example, float store, float add, and so on. So all of the floating point instructions will begin with an F. In addition, most floating point instructions, as I mentioned before, operands. Most of these instructions operate on the stack top or a combination of the stack top and values in memory. These could be floating point or integer values in memory. And then finally, no floating point instruction can transfer data between a general register and a floating point register. So no transfer between CPU and FPU registers. Now, I say this, there is one exception to that, and we'll talk about that a little bit later. But for now, let's go ahead and get started with our instructions. We'll start with some of the more basic instructions. Float load will do essentially what it sounds like. This will load the stack from various locations. So float load, real memory operand, is going to load stack top with whatever floating point value you have indicated. The interesting thing though, load stack top, we could almost say push stack top, and then we'll say that the values on the stack are pushed down, as we would expect. Okay, float integer load. This will do the same thing. This loads stack top load, with some integer value stored in memory that you indicate here. Again, values on the stack will be pushed down. Finally, well, not finally, we've got several of these. float load some value that's already existing on the stack. This is going to push a copy of whichever one of the stack registers you indicate to the stack top. Okay, some more float load instructions. First one, pretty obvious. This one's going to push 1 to the stack top. This one is going to push 0 to the stack top. And you might say, gosh, why would we ever use things like that? Well, what if you have to initialize a sum or a product? This is an easy way to do it while you're executing a floating point segment. Float load pi loads pi. So pi goes to the stack top. Fnet is not a float load, but it is the initialization. This initializes the floating point processor, clearing the stack. Now, clearing the stack, but when we look at this in the debugger, we're not actually seeing live representation. It kind of freezes execution at the time our code is running, but other code is running in the background, also using all of these registers and processors and instructions, so we don't actually see the actual registers. If we did, we would see that they were cleared after Fnet. Okay, now before we go on, I'm going to start some examples, but I want to point out to you that there are several figures in the book that have additional instructions, and also goes over these instructions as well. Figure 9.2 has some of the additional float load instructions. Alright, so let's say we have cleared our stack, there's nothing on it, and we say float load 1. Well, float load 1 loads 1.0 to the stack and pushes everything else down. Well, nothing else is there, so we're okay. Let's say we also want to load a floating point value and an integer value. Let's just say float val equals 8.2 and int val equals 5. Oh, we'll just do something interesting like that. So when we say float load, this floating point value is going to push that value from memory onto the stack, 8.2, and it will push everything else down. Same as with integer load. This is going to load the integer value 5 that is promoted to a floating point value, an 80-bit floating point value, pushing everything else down on the stack. And then, in this case, I want to load or copy, take a copy of what is in ST2, push it to the top of the stack, and push everything else down. Okay? So, kind of gives you an idea of some of the basic operations. So that's float load. Let's look at float store. Store instructions are going to copy the stack or stack top or other parts of the stack to a destination. So for this first one, float store, I want to take whatever the stack top is and copy it to memory. So stack top, whoops, stack top goes to memory. In this case, I have a special version of float store that has a P suffix. This means pop the top of the stack when you're done. So in this case, this has two things that happen. Stack top goes to memory, and then we pop the top of the stack. Okay? Integer store stores stack top to someplace in memory. Now it's an integer value in memory, so it's going to convert stack top to integer, or demode it to an integer value before it stores it. And again, this is the same as integer store, except now we are popping. So stack top goes to memory, and then we pop the top of the stack. Okay? All right, a few more instructions, and I'll use different values. Oh well, we'll assume these values. Here are our values from the last time, but now I want to take the stack top and store it in several different places. Okay, so float store is going to take stack top and move it to float value. So 1.0 goes to memory. This is not going to pop the stack, so everything that's on the stack now will remain on the stack. Okay, this will do the same thing. It will pop the top of the stack. Well, I shouldn't say that. It will copy stack top into float value. Then it will pop the top of the stack. Then an integer store is going to take stack top, going to convert it to an int, store it in memory. It will leave the stack unchanged. And then again, this one has the p suffix, so we will store stack top into int val, demoding it, and then pop the top of the stack. So we're left with 50.2 and 1.0 as a result. Okay. Well, just to kind of wrap up kind of loading and storing, let me just talk a little bit about the exchange instructions. Got two versions. F-exchange exchanges the values in stack top and stack top 1. So exchange stack top and stack top 1. This is going to exchange stack top and whichever other stack register you indicate. So that's very similar to the exchange instruction we're used to seeing, but it has, again, some inferred operands. All right, let's do one more example. We want to exchange stack top with st1. When we do that, the result will be the following: 1.0, 50.2 on the stack. Okay, now it's time. So for the addition instructions, we have a series of instructions that we're going to go through. These, you'll start to see some patterns emerging in some of the arithmetic instructions. Okay, in our first one, fadd has no operands. What this does is actually several things. It first of all will pop stack top and st1, so the first two registers. It will add them together, so calculate sum and then push that sum on the top of the stack. Okay? Alright, now we start to look at some operands. In here we notice for the first time that we have both the destination and the source. This gives us some help because this is going to add stack top and whichever other stack register you indicate, but it's going to store it in stack top, since stack top is our destination. Likewise, in this case, st_num will be overwritten by the sum stack top plus st_num, whichever number you indicate. Okay? Now, finally, we have fadd with our p suffix again, so we're going to pop the top of the stack. In this case, stack top, whichever number you indicate, will equal the sum of stack top plus that register. And then pop stack top. So guys, and I didn't mention this before, let me mention it now. The p suffix gives us a way to clear up or clean up the stack as we go. So instead of, the book mentions the fact that you can use finit to clear things out, that you can, it's really bad practice. You would much rather pop things off, clean up the stack as you go. So this really makes you think about traversing your instructions with the mind or the idea that you're going to be operating as a stack. Alright, we've got a few more add instructions. This first one is going to add stack top plus whatever value, floating point value you indicate in memory, and replace stack top with the sum. This one is going to do an integer add, so stack top plus whatever int value you indicate from memory. Again, this will replace stack top. Alright, now let's do some more examples. So in this case, I have, just pretend I've initialized the stack, so I've done an finit, and then we've loaded some new values on the stack, and maybe these are values that we've loaded from memory. Okay, so our first instruction is going to pop stack top and st1, add them together, 15.5, push that on the top of the stack, and in this case, let's throw another value here and say 2.0. So 2.0 is going to be here. In this case, what we're going to do, we're not going to pop anything off. We're simply adding stack top and st2, so 15.5 plus 2 is 17.5. Stack top is my destination, so that's where the sum is going to get replaced. Everything else will remain the same. And then in this case, we're just going to do the same thing, but reverse the order of our operands. So, and we're going to pop the top of the stack. So I'm adding stack top to st2, so 17.5 plus 2.0 is 19.5. It'll replace this, but remember, we're also going to pop the stack top off, so it's going to be 1.25 and 19.5. And then here I'm going to add, and let's say int val has some value in it. We'll say 10. Now I'm going to do an integer add with stack top and int val. This will replace stack top. So 10 plus 1.25 is going to give me 11.25 and 19.5. Okay. So here's where we start to notice some similarities. Although you have to realize other similarities will not be the same, or other similarities won't exist. F sub, as you can imagine, this is going to pop st1, this is going to subtract. So it's going to calculate ST1 minus stack top, and then push the difference to the stack, to the top of the stack. Okay? Alright, F sub, ST number and ST, again I have a default destination. So let's just say ST num is going to be overwritten by the difference ST num minus stack top. In this case, my destination is the stack top, so stack top will be overwritten by the difference ST minus ST num. Okay? I can also have some values in memory as operands. So in this first case, I'm going to calculate ST minus my real value. This will overwrite ST. So ST minus, whatever float value we indicate. Integer subtract. This is also going to, this has, we can use some integer value stored in memory as our source. However, the destination implicit, again, is stack top. So this is going to calculate stack top minus whatever integer value in memory you indicate. And in this case, I see the P suffix. This will do the same thing. So stack top number is going to equal stack top number minus stack top, and then it will pop stack top after that. Okay? Okay. So, I mentioned before that some similarities do not exist. So, in addition, we know that if we add 3 plus 5, that is the same as 5 plus 3. So, commutativity exists. Commutativity does not exist for subtraction. 3 minus 5 does not equal 5 minus 3. Okay, so because of that, I have some reversed subtraction instructions. These will do the same thing that the previous instructions did, however, the order of the operands will be reversed. So, F sub R is going to pop stack top at stack top 1. It's going to calculate stack top minus stack top 1, and the difference will be pushed on the stack. Okay, F sub R. Again, this will reverse these. However, my destination is whatever number I indicate. It won't be stack number minus stack top. It will be instead stack top minus the other register you indicate. In a similar fashion, stack top will equal stack top number minus stack top. Okay, a few more. Again, work very similarly. These will overwrite stack top, but instead of ST minus float value, it'll calculate float value minus ST, and the difference will be stored at the stack top, or overwrite the stack top. Integer subtract, stack top equals int val minus stack top, so stack top is overwritten by the difference. Notice how handy these are. I also have the P suffix here as well that allows me to pop the top of the stack. So this is going to be stack top number equals stack top minus stack top number, and then this will pop the top of the stack. Okay. Alright, let's quickly hit some multiplication. Again, the patterns emerge here, and we'll note that this is going to pop stack top and ST1, calculate a product, and then push the product to the top of the stack. Okay, this is going to multiply the stack top by another register, with this register being the destination. So this is going to be stack top number times stack top. And in this case, similarly, so you see we have quite a bit of variation, but you see the patterns in the instructions. This is going to be helpful for you guys as we look at our next assignment and we move into our final exam, where you're going to need to remember what the operand possibilities are for these instructions. The fact that they are very similar helps. So fmol real memory operand, this is going to multiply the stack top by that real value, replacing stack top with the product, stack top times float val. This will do the same thing, except with some integer value you've stored in memory. Okay, I see my P suffix here. So stack top number is my default destination. We'll have ST number times stack top, but then it will pop stack top. Okay, division. Guess what division does. Again, you're going to see now similarities between multiplication, but also big similarities between division and subtraction. In that division, we're also going to have the reversed versions of the operations. So this first one is going to pop ST and ST1. It will calculate the quotient, and then quotient will be pushed to the stack top. Now, I say quotient. Let me tell you what it does. It calculates, and let me just say right here, it calculates ST1 divided by, divided by stack top. Just to make that clear. Okay? Alright, again, I've got a default destination, so stack top number will be replaced with the quotient that results from STnum divided by stack top. Okay? And likewise, stack top will be replaced with the quotient that results from stack top divided by STnum. Okay. Real memory operands, integer value operands, and then I also have my pop option. So this is going to replace stack top with the quotient ST divided by whatever floating point value we indicate. Integer division will replace stack top with stack top divided by that int val. Okay, and this will overwrite stack num with the quotient that results from stack num divided by stack top, and then pop the stack top off. or pop it from our register stack. So, as I mentioned, we also have the reversed division version or division instructions. These do the same thing that we just went over, except the order of the operands is reversed. Very handy. Alright, let me show you a few miscellaneous. I know this segment is long, I apologize for that, but let me just show you these miscellaneous instructions. They can be handy quickly. Floating absolute value, this is going to replace stack top with its absolute value. Change sign will replace stack top with a negated stack top. Float round to int, round stack top to an int value. Okay, and then f square root, stack top will be replaced by the square root of stack top. I will also mention that there are also some trigonometric, exponential, logarithmic functions. There are a whole bunch of other floating point instructions that we won't have an opportunity to get to. So I'm going to save the comparisons for the next segment. We'll start with those.